diagram book across a table with a horizontal applied force of 15 newtons. If the coefficient of kinetic friction between the block and the table is 0.35, find its acceleration. So here is the table, and I almost always just draw a block to indicate whatever it is. The block has mg down, normal force up. There's a horizontal force on applied force, so I'll just call that F. And then kinetic friction is going back to the left. So there's a lot you can say. F. We can call it force applied, force kinetic, and so on. Is this something you've seen before? Is there anything here that is not familiar?
Yeah, you got that. You get the force on the right, which force is that? The one going forward that she's pushing?
That's the horizontal applied force of 15 newtons.
Okay, so that's horizontal applied. We got the normal force going up, and then we got the gravity pushing it down.
Mm-hmm.
Then we got friction going to the right. So this all makes sense so far.
To the left. It opposes motion because a lot of the acceleration is going to the right, if there is any. Okay.
Mm-hmm.
So the first thing is you can say, okay, sum of the forces in the x direction equals mass times acceleration.
Mm-hmm.
We'll choose right to be positive. So we have the force applied minus the force of kinetic friction equals mass times acceleration. Mm-hmm. Now, I'm not sure how comfortable you are with symbolic, but most physics problems are done symbolically, and then you put the numbers in at the end. You could definitely start putting numbers in now at this point. It's up to you. How have you been doing it in class, or what's your comfort level with doing it symbolically?
My comfort level is just kind of like writing out how we're gonna do it, like with the symbols, and then we substitute it with the numbers, and then go from there.
Okay, because you generally write at least both of these. Some of the force in the y direction, some of the force in the x direction. In the y direction, is the box accelerating? Is it moving up or down at all?
Force accelerating? It's you got the normal force going up and the gravity pushing it down.
Right, but is it in motion? When you're pushing the box to the right, is it in motion up or down?
It's in motion to the right, right?
That's correct. So there's no acceleration in the y direction.
Okay.
In this problem. Because if you're just pushing something to the right, it's not going up or down. It's just going to the right. Mm-hmm. Is that okay? Because that's very important here.
That's okay. Yeah.
Okay. There's the normal force is up. We'll choose up to be positive. Minus mg down equals 0. Okay. Is that okay so far?
Yes.
So the normal force is mg in this problem. From class, do you remember what Fk is?
Fk, something with friction?
Yeah, it's the coefficient of friction times the normal force.
Oh, mkn, so that's what that is. All right. I didn't really understand what that was today.
Well, in this case, n is mg, but it's not always mg. It could be other things. So you're gonna take this and substitute it in over here. So you have force applied minus mu k mg equals mass times acceleration. Now we've done a lot of things here. We're trying to find the acceleration of the box. So if we solve for a equals the force applied minus mu k times m times g over m. And we know these values. The force applied is 15. Mu k is 0.35. The mass of the box, or in this case, the book 1.04. Gravity is 9.81, all over 1.04.
Okay.
That's it. So you have to get that value here. I could definitely calculate that as well.
We'll do that right now. Let's see. So I ended up getting 10.89 for this.
Okay. I got 10.99, 11. So, okay. Anything to follow up on that? I mean, that's it for that question.
Nothing to follow that up. Let's go to number 2.
Let's go to number 2. So number 2 is more complicated. I hope you got a few practice problems on these before just straight into this, because like you really need to do a few of like number 1 before you jump to number 2. Part of this is being able to draw the picture. It's kind of like going back to geometry, and if you can draw the picture correctly, you can do these problems. So there's a ramp. There's a box on the ramp. It's 38 degrees. And it's placed on the ramp. What is the magnitude of the component of the weight that is parallel to the surface ramp? So this is a little bit complicated. There's mg down.
Yeah, and we still have normal force going up, right?
The normal force, though, is going perpendicular to the plane.
Oh, okay.
Which is different. The choice in most of these problems is to rotate your axes. Normally your axis is like this, but we're going to rotate it so that your axis is parallel to the ramp and then perpendicular to the ramp. So this is your x, this is your y. I'm sorry, this is your x, this is your y. So the normal force is still going in the y direction. But the problem is mg is not. Mg is actually going, it has both a component in the x and the y direction.
Okay.
And there's a lot that goes into this. This is a trigonometry thing. It's a physics thing. But mg has a component that is in the y direction, and then a component that's in the x direction. So this 38 degrees actually becomes this angle up here.
Oh, so we switch it over? Okay.
Yeah, and again, there's kind of a few things that go into that. I mean, there's videos out there that show this, but this is now 38 degrees.
Okay, that makes sense.
So you have the hypotenuse. So if you want to find the x component and the y component here, you have to use some trigonometry. If you take the cosine of 38 degrees, this equals the adjacent, which is y, over the hypotenuse, which is mg. So if you solve for y, you end up getting mg cosine 38.
Oh, all right. All right.
And now if we go the other way, if we say, okay, well, what's sine 38? Well, sine 38 is x over mg. So x is equal to mg sine 38. So this problem is asking for the magnitude of the component of the weight that is parallel to the surface. So they're asking for this means the x component of gravity, of weight. I'm sorry, of weight. So they're really asking for this one right there that's heavier, and they're asking for that, which is over here to the right. It's the x equals mg sine 38. So that's 22 9.81 sine 38 degrees. I just need 30 seconds. I'll be right back. Hey, Jack, I'm back. Did you get that calculated?
I haven't calculated it yet. Put that in right now. All right, so 22 times 22 9.81 then sine 38. I end up getting 132.87.
Okay, so we'll call that 132.9 or 133 newtons. Now I know it doesn't ask for it, but let's calculate the y component. The y component of weight. In this case, y is mg cosine 38. So that's the 22 again, the 9.81 times the cosine this time of 38.
All right, 9.81 cosine 38. All right. There we go. And, I end up getting 170.1 newtons.
Good. That's all it's asking for in this problem. There is acceleration, but it's not asking for it. So you'll probably do a lab. Well, actually, you're not in school. There's almost always a lab where you put something on an incline and you bring
the lab.
Well,
yeah, I did that.
Well, if you bring something up on an incline, the box will slide down, and that's a pretty common lab that is done here. That's it for number 2, though. So we can move on to number 3.
All right. So the answer is what does it ask for again? Like the beginning of the second question.
It asks for the component of weight that is parallel to the surface of the ramp, and that's the first one, the x component.
Oh, it's just the x component?
Yep, that's just this one right here. That's parallel to the surface is that right there.
Oh, all right. So it'd be just 132.9 newtons is the answer for that.
Yes.
And so we did the y component to see like
just so because you're gonna eventually need to do it. I mean, you have to do it in another problem, but
all right.
So, all right, 54.3 kilogram block is placed on an inclined plane that is 42.4 degrees from the horizontal. What is the acceleration of the block? This is an important place for me to make it known that I choose to draw my inclined planes like this. You could just as well see them the other direction, but we're gonna do it this way. So there's a box here. It has a mg down. It has a normal force perpendicular to the incline, and this mg is broken up into going to have both an x and a y component to it. The 42.4 degrees is here, and that means it's also there, 42.4 degrees. So just like in the previous problem, you're going to have to calculate the x component of gravity and the y component of weight, not gravity. I keep saying that. So so you can draw the triangle if you first few times sometimes you have to draw the triangle over here. That's fine. The 42.4 is there. This is mg. The x component and the y component here.
All right.
The x component is again just like before. It's mg sine the angle 42.4. So this time the mass is 54.3. Gravity's 9.81. Sine 42.4.
That 42.4?
Yes.
All right.
The y component is the same thing. You want to get that as well, and then we'll talk about how to use these. But it's kind of like finding the x and y coordinates of velocity when we're shooting cannons off a hill. You end up doing this in almost every problem. So you want to get really comfortable with these calculations.
Okay.
Let me know when you're caught up here, so we can talk about what the problem is actually asking for.
All right, so I got for y component we get what is it? 393.4.
Okay. So if we go back to our our picture here, if you put a block on a ramp, which way is it going to accelerate? Up or down the ramp?
It's going to go down the ramp usually, right?
So I like to draw that down. I like to draw that's the way it's going to accelerate. Okay, so now we can do some of the forces in the x direction and some of the forces in the y direction. Because we're using a rotated axis, okay, the sum of the forces in the x direction is along the incline, okay? Now here's another thing that I think is very important here. I always choose the direction of acceleration to be positive. Like, and you're used to positive being to the right. You can choose the direction of acceleration to be positive. Mm-hmm. So in this case, if it's going left, it's positive. So do you see how mg down here is going to the left, the x component?
Yes, I do.
So that's positive. So that mg sine 42.4, those 359 newtons, we'll just throw that number. It's going to the left. So it's positive. Are there any other forces going to the left that I've drawn here?
Just the acceleration, right?
And that's over here on the right. So that equals mass times acceleration. Mm-hmm. Do we have the mass? Yeah, the mass is 54.3.
Mm-hmm.
And we don't have the acceleration, but we can calculate it.
How do we calculate the acceleration in this case?
We're solving for A. This is an equation. It's just you're going to divide both sides by 54.3.
Oh, all right. 359 divided by 54.3. I get 6.61.
Okay. Now, if we were to find the sum of the forces in the y direction equals mass times acceleration, this is super critical that you understand this. In the y direction, vertical, perpendicular to the incline, is it moving in perpendicular to the incline? Meaning, is it moving along this sort of dotted line here? Is it moving that way?
Yes.
No.
No.
It's only moving in the direction of acceleration.
Oh, okay.
So the mass times acceleration is 0. So doing anything in the y direction doesn't help you find acceleration because there's nothing going on in the y direction. It's not moving in the y direction. It's only moving in the x direction. The x direction is along the incline.
Okay.
All right. We ready to go on to number 4?
Yes.
All right. Number 4 takes information from number 3. I mean, Jack, this is tough stuff. I mean, if you haven't seen this before, a lot of things I'm saying are they're just not going to mean much, and it's normal. It's a tough class, so keep trying here. So we got a block. It's on an inclined plane, but this time there is friction. Okay, but we'll worry about that in a moment. Mm-hmm. mg down. mg is always down. Normal force is always perpendicular to the surface. Okay. If it's in motion, which way is it going to accelerate?
Down the incline,
the block,
right?
Down the incline, in what we're going to call the x direction here.
Mm-hmm.
Okay. Very important. Friction. Friction almost always opposes motion. Or in this case, it opposes the direction of acceleration.
Mm-hmm.
So if acceleration is to the left, which way is friction going?
Is opposing it, going up.
It's going to the right or up the ramp. I like drawing it down here at the bottom. I mean, some probably books don't. Kinetic friction. You can. I don't know. There's a lot of ways you can denote friction. I actually don't know what most books use. So we need to find the acceleration, right?
Mm-hmm.
But that's kind of down the road. You're going to have to find the x and y components of weight here. This is 42.4 degrees. That means this angle up here is also 42.4 degrees. You've got to find the y component and the x component of weight. Luckily, those are the same from before. So the weight in the x direction, weight in the y direction. Let me scroll up and grab those values. They're the same as in the previous problem. Nothing has changed on those. In the x direction, it's 359. And I think that was 393.
Mm-hmm.
Okay, so you get a chance to redeem yourself here. Sum of the forces in the y direction equals mass times acceleration. Is the block moving along this vertical line that I'm drawing?
Is the block along the vertical line? No, it's only moving in the A direction.
So this means it's 0. Okay, now let's look at all the forces that are vertical, meaning like along that dotted line. There's normal force and there's weight in the y direction. Do you see anything else?
Not at the moment.
So that's it. Those equal 0. So the normal force equals weight in the y direction, which is 393 newtons.
Okay.
Okay. Now let's go in the x direction. In the x direction, there's several forces here. Again, you want to choose the direction of motion as positive. So since it's going left, left is positive. So this weight in the x direction, it's positive. Weight in the x direction is positive, minus the kinetic friction in the other directions, it's going to the right, equals mass times acceleration. Is that okay?
Yes.
So the weight in the x direction, let me give us some more room here. Weight in the x direction is 359 minus the kinetic friction is mu k n equals mass times acceleration. The coefficient of kinetic friction is given as 0.25. The normal force is 393. The mass of the block is 54.3. And we're trying to find acceleration. So you got to do this calculation, divide by 54.3, and you'll get your acceleration. Let me calculate that as well.
I got 4.8.
Right. Good. Now, how does that compare to the acceleration that we found in the previous problem, 3?
It's a little bit slower.
Does that sound reasonable to you that because of friction, it's going slower, it's accelerating slower?
Yes.
It does.
Because there's a constant force that's slowing it down.
It's opposing it, yeah. Exactly. Okay. Anything to follow up on that before moving to 5?
Not at the moment.
Okay.
No.
All right. Now five is how your instructor, and a lot of instructors is they say, okay, we're not going to let you forget what you learned in one-dimensional or two-dimensional motion. So they're saying, okay, here's a plane, the inclined plane. It's 5.2 meters long.
Mm-hmm.
They're assuming your box is up here, and they want to know how long does it take to reach the bottom of the plane. Okay. They're asking for time, which we haven't talked about in a long time. Which equations do you have time in it?
What is it? I don't remember.
So x equals x naught plus v naught t plus 1/2 at squared. Do you remember that?
Mm-hmm. Yeah, I do.
Okay, so this one, and I remember I said, there's problems where you throw something up and it's always gravity, but horizontally there's no acceleration. Well, there is acceleration. This thing is accelerating. Like imagine, I know it's on a ramp, but imagine you're standing at the top of the ramp and you're just looking down it. You only see, your world is just this straight line down.
Mm-hmm.
Okay, so this whole thing here, this whole thing that we're doing here, it's the same as you standing right here. You're instantly accelerating to the right 5.2 meters. It's the exact same problem.
Okay.
Okay, so let's say where you start, let's call that 0. What does that mean for x0?
Is it 0?
0.
Doesn't matter.
In this problem, you are assuming, and this is an assumption that like you have to make, the initial velocity is 0. It's not moving when it starts.
And you got 1/2 acceleration times time squared.
Right. Now, do you know acceleration? Yes, you just found it in the previous problem. So let me rewrite this. It's x equals 1/2 at squared. You know the acceleration. You just found it. Acceleration is 4.8. X is 5.2. And then you're solving for t.
Oh, okay. All right, so I end up getting for time 1.47 seconds.
I agree. All right, Jack. So where do you want to go from here? We got some time left.
Oh, we actually have time left.
Yeah.
I think I kind of want to end it here because this was kind of all I wanted to work on today.
All right. Well, sounds good. I will send you the notes and the video here shortly.
Thank you, Matthew.
You're welcome. Have a good night.
Appreciate your time. Bye-bye.
Of course. Bye now.